Swayam Prabha. Digital India. Educated India.
Welcome to the course on advanced machining processes. Today I am going to talk about a very important and useful process known as laser beam machining process. It is abbreviated as LBM. The talk is organized as follows. First I will give the introduction to the laser beam machining process, then laser types of the lasers, process characteristics, applications, and then conclusions. Introduction and working principle of laser beam machining process. Now I am going to give you a very interesting experiment that you also must have done when you were a child. You take a lens, and with the help of a lens you concentrate the sun rays on a piece of paper. Especially when sun is bright, you will find that after some time the piece of paper starts burning. What is this going on? That means you are utilizing the sun rays which are concentrated at a small point, and the heat intensity at that particular point is so high that it starts burning the piece of paper. And the question arises, can we make constructive use of this phenomena in general and in manufacturing in particular? Now exactly on the similar thoughts, a very important manufacturing process that is known as laser beam machining process has been developed. Here you have a laser gun, with the help of laser beam is produced, and that laser beam is focused in at a very small point having a very small diameter, and that focused beam has so high intensity that you can burn or melt any material known to us. Even diamond can be melted by this particular process, and it has been used for cutting or drilling a hole in the diamond. As you can see, here is the workpiece and here is the concentrated light at a particular point, which is utilized for melting and or vaporization. So, this tells you in very brief the working principle of laser beam machining, that is, you are utilizing heat produced by laser beam, and this heat is utilized for melting and vaporization of the workpiece material. Now, the question arises, how to produce a laser? Hypothesis of Einstein, I will tell you, he proposed that it is possible to use light energy to stimulate electrons that would emit light of same characteristic. This particular hypothesis had been used to produce the lasers. Consider an atom that is brought to high energy level E2 from energy level E1 by outside energy source. This outside energy source can be light, it can be heat, it can be electricity, or some other appropriate outside energy source which will stimulate the atoms in the lasing material from energy level E1 to the energy level E2. this atom is then allowed to decay back to ground state energy level, that is from E2 level to E1 level. As a result of this decay back, a photon is released by the material, and this photon is nothing but the light. This photon contacts other atoms in the lasing material. This atom will also decay back and release a photon. That means, this atom also will go first to E2 level, and from E2 level it will decay back to E1 level, and it will release another photon, and this leads to chain reaction that continues, and stimulated emission of photon keeps taking place. Now, as a result of this, you will have large amount of photons in the lasing material, and this sequence of triggering clone photons from stimulated atoms or molecules is known as stimulated emission. And energy source, this energy source is usually so powerful that most of the atoms of lasing material are at higher energy level, that is E2 level, and release of photons when they are decaying back, and this process keeps going on. As you can see here, the same thing is shown here in the schematic diagram. Here is a absorption of energy, and then from this Q level it moves to the P level, and when it decays back to the Q level, it releases the photons. So, this transition by absorption and spontaneous emission between two given levels of an atom, that is from Q level to P level. Same thing what I was telling, that from energy level E1 to E2, or here it is shown from energy level E1 to E3, and then decaying back to energy level E0, that is here in place of E1, here it is given as E0. From E0 it is going to E3 and back to E0, and it releases a photon. Now, for actual production of lasers, you need what is known as feedback mechanism. Here you have the lasing material or lasing medium as shown over here. This can be the solid or the gas mixture, as we will discuss later on, and there are two mirrors as shown here on the left side and the right side, and for stimulating the atoms of lasing material, you have the energy source. This can be the electricity, heat, light, or whatever it is, but it has to be appropriate energy source. Now, when these photons are moving in the lasing material, they go out, and here is the material, here is the mirror, and when they strike this mirror, one is the fully reflecting material, another is normally a partially reflecting material. And what will happen from this fully reflecting material, the photons will again go back to the lasing material, and if it is the right side, if it is a partially reflecting material, then part of the laser, part of the photons may go out, and that will form what is known as laser beam. We will discuss it little later also. So, what happens that in feedback mechanism, it captures and redirect a few coherent photons back into the active medium, that is the lasing medium. Then it stimulates the emission of some more photons, that I have already explained as a chain reaction. Also permits a small percentage of coherent photon to exit as laser light, as I mentioned that on the right hand side, suppose it is 95% reflecting, then from 5% whatever is this part of the laser beam will be exiting or coming out of it, that will be utilized for various purposes. So, this is known as laser by the name light, its full form is light amplification by stimulated emission of radiation, that forms what is known as today as laser. So, one of this is 100% reflecting. So, no laser light is passing out of it, as I have explained. Now, what is the working principle of laser beam machining process? What you have here is the energy input in the form of heat, electricity, light, etc., and then this energy input is to the lasing medium. This lasing medium may be solid, it may be liquid, and then finally, what you have is energy in the form of laser beam useful for various activities. It can be manufacturing activity, it can be medical activity, it can be for other activities also. As you can see here, when a pointer is being used in the classroom, that is also having a laser light. So, it has various activities in different spheres of the life. Electrodes are kept at both ends. I will explain you how the laser being formed in the gas medium, that will be shown to you in the following slide. In this slide, you will find that the electrodes are kept at both ends of the tube. Electric current stimulates gas or other lasing medium atoms or molecules in the tube, and then there is a feedback mechanism, as I have explained in the earlier slide, that consists of a set of parallel mirrors at the ends of the tube. One mirror is fully reflective, while another mirror is partially transparent, which gives laser beam as output useful for various activities, and laser light is monochromatic in nature. This is very important characteristic of laser light, as in contrast to the sun rays or sunlight. Now, this is where I told you that it has two mirrors at the end of the tube. There are two, see, this is known as folded resonator axial flow carbon dioxide laser, and you can see here there are two mirrors. One is written here, highly reflecting mirror, and there is another mirror from which you are getting a laser beam. Now, there are two tubes, you can see here there are two tubes, one is this tube, another is this tube. Here the you have the gas lasing medium as the gas in both the tubes, and those photons are created and they come, and here are the two turning mirror, and that photons or the light gets reflected from these two mirrors. From this, when it comes from this tube, it gets reflected from this mirror and then again reflected, comes to the another tube, where again production of photons takes place, and finally a part of the photons come out as the output mirror. Here you have the two cathodes, as you can clearly see here, and these are the anodes in the tube, and production of laser is taking place, and this is useful for comparatively high power lasers. You can have more than two tubes folded, more the higher the power that you need, and more number of the tubes you will have to use. Wavelength varies in a narrow, very narrow range of the spectrum. This is the speciality of this particular laser beam. A simple lens focuses and concentrates laser light in a very small diameter and high intensity, and this is known as laser beam. Laser light is coherent, it travels in phase and low divergence. This is very important characteristic. The divergence of the laser light is very small compared to normal light. Use of laser in material processing requires high power density laser. Now, there are certain applications, as we will see later on, say for example, the metrology applications, where you do not need very high power density lasers, a small power density laser can do, but there are certain applications, as we will see, that like cutting, you need high power density lasers. Machining operation requires 1.5 into 10 raised to power 6 to 1.5 5 into 10 raised to power 8 watts per centimeter square laser heat intensity, which is very high. Workpiece is kept very near to the focal point of the laser beam, because closer it is, more intensity of the heat it will have and higher efficiency the system will have. Then laser beam and depth of focus. Now, normal light you see that the focus is at a particular point, but laser beam has a certain length over which you find more or less the same heat intensity or the density, and as you can see, that is why it is shown as delta f as the depth of focus. This is the minimum spot diameter where you can get more or less the same diameter in this particular length, and there is a focal length f, as you can see here, where the beam which is coming from the left side, it gets concentrated or maximum intensity is given over there. Now, another important point you can see here on the left side, that the divergence angle is very small. Beam divergence angle is very small compared to normal light, and this is a characteristic which is useful. Now, another point which is to be looked into is that there is a laser beam, and if you take the cross section of this beam at a focal point, you will not have heat intensity same at every point across the cross section of this laser beam. As you can see here, this tells you the intensity of the heat across the laser beam. It is maximum in the center and it gets decreasing on either side of the center of the beam. Now, there are various parameters with the help of which you can specify the laser beam. That is, first thing is wavelength of the laser beam, spatial mode structure, brightness, position, beam waste, polarization and spot size. Now, in various applications of laser beam, many times gas is utilized for assisting the laser beam activities. Now, the system or the arrangement of the gas is as shown here in the figure. Here is the laser beam which is getting concentrated with the help of the focusing laser on the workpiece, and whatever heat is generated, that is resulting in melting and vaporization of the workpiece material, and to help in the ejection of the molten material and oxidation of the material, workpiece material, you can use this particular gas arrangement as shown over here, that gas is being supplied through the ports, and this comes along with the laser beam and helps in the laser activity or laser beam machining process in this particular case, and this gas is supplied with the help of a nozzle as shown over here. Now, materials parameters which affect the performance of the laser beam machining. Now, this is very important that while selecting laser beam machining, we should pay special attention on the properties of the workpiece material, otherwise you may not get the desired result, because for certain materials, as we will see later on, like copper or aluminum, laser beam machining is not very effective. So, we should consider the properties of the workpiece material as reflectance, absorption coefficient of the workpiece material, specific heat of the workpiece material, thermal conductivity, thermal diffusivity, latent heat of melting of the workpiece material, latent heat of vaporization of the workpiece material, transformation temperatures and melting temperature of the workpiece material and vaporization temperature of the workpiece material, because all of these parameters will decide how much heat you require for machining purposes, or even say for example, for welding purposes, you require. So, and then phase transformation. So, what happens really, you should consider all these parameters of the workpiece material, especially as I just mentioned, materials like aluminum cannot be efficiently machined because it is not in favor of laser beam because of so many properties it has. Now, there are various thermal processes that are taking place during the laser beam machining, just like absorption, which depends upon skin depth, penetration depth, and heat transportation, which is a function of thermal conduction, then rise in temperature of the workpiece material. It also decides heat affected zone and heat penetration depth and melting. Then evaporation, again as I have mentioned already, depends upon the thermal properties of the workpiece material like latent heat of evaporation and melting temperature. Surface cooling, ablation are some of the things or some of the events or some of the thermal processes that take place during laser beam machining, and they are shown over here. Here is the laser and the absorption of the heat is taking place as shown by 1, and then there is the heat transportation taking place, and third is the temperature rise that is shown over here. Heat is transported, taking, conducting away, radiated away and so on, and temperature rise takes place, and then there are some evaporation of the workpiece material that takes place. So, those thermal processes are represented in this particular diagram. Now, this is very important figure over here as long as laser beam machining is concerned. Now, laser beam, it can be a continuous laser beam or it can be a pulse laser beam. Pulse laser beam is also of various types, which I will show you little later on. Now, pulse laser beam can be long pulse lasers and short pulse laser, which depends upon its time scale, which we will discuss later on. Now, what happens if you are using long pulse lasers for laser beam machining purposes? You can see here this figure very carefully that there are various kind of defects that arise. Here you can see there is a long pulse laser beam. Now, when it is melting and drilling a hole in the workpiece material, you can clearly see various kind of the problems like micro cracks are developed over there, as you can see over here. Then there is a heat affected zone which is being produced, as you can see by a specific color over there. Then this is the melt zone where material, workpiece material has melted out due to the concentrated high density heat produced by the laser beam. Then there is a recast layer, and as I have mentioned in my earlier lectures also, that these thermal processes have this basic problem like EDM, electric discharge machining, laser beam machining, they produce the recast layer which is shown over here also, and this layer should be removed before this part is put in the device. Then there is a surface ripples due to shock wave near to the groove or the hole or the fissure being created, as you can see clearly over here, and then damage caused to adjacent structure. Suppose this is some structure or some other things that you have made already, and if grooving is taking place near to this, this will get damaged as shown over here. Then surface debris, whatever material is removed, when it gets solidified, it is known as surface debris, and they will get deposited at the top surface of the workpiece, and many times it becomes difficult to remove them. And then you have the ejected molten material which converts, solidifies and gets deposited on the surface as the form of surface debris. Now, heat transfer to surrounding material also takes place, and because temperature is very high, definitely you will have the radiation losses also. So, you can see here there are the problems when you are using the long pulses, so many problems which are shown here. Now, on the right side if you see, here is a diagram which shows the machining or laser beam machining with ultra fast lasers or short pulses. Now, you can see clearly here the size of the pulse is very large as can be seen here, but here the size of the pulses is very small, and that is why it is known as ultra fast laser or ultra short pulses. Now, if you compare left hand side figure with the right hand side figure, you do not find most of the weaknesses of the left hand side figure in the right hand side figure, because you can see here there is no melt zone shown over here, and there are no micro cracks, no shock wave is shown over there, no hot, dense, non-electron soup etc. plasma is there, no heat transfer to the surrounding material, and there is no damage caused to the adjacent structure, and there is no recast layer. So, this simply indicates that for accurate precision machining with the help of laser beam machining, one should go for ultra fast lasers or ultra short pulse lasers if economics permits, because this has to be decided based on the economics of the process, because there are certain jobs which really do not require that kind of accuracy or the tolerances. Then why to go for ultra fast lasers? You can go for long pulse laser or even for continuous lasers rather than pulse lasers. So, all this will depend upon the requirement of the job and the economics of the process. Now, you can clearly see there it was shown as a pictorial view. Now, here are the same thing shown with the actual photographs of the feature or the feature created by long pulses and short pulses. As you can see here left hand side, these are the, this is the photographic view of the hole being created in a workpiece material, and you can see the irregularities on the edges of the hole created and deposition of the recast layer and the debris that is clearly seen visible over here. While on the right hand side, this is the hole created with the help of short pulses, and this is very neat and clean as compared to the left hand side hole that has been created with the help of laser beam machining. So, it clearly indicates the importance, accuracy and precision that you can achieve with the help of ultra short pulses or short pulses as compared to long pulses and continuous laser beam machining. Now, this laser beam machining system carries not only the laser gun or the device for producing the lasers, there are other features or other parts of the laser beam machining system as shown over here. You have a laser producing gun or system, subsystem, and then there is a beam delivery system. This is M, not N, beam delivery system, and then there are nozzle or the lens with the help of which you are concentrating the laser beam on the workpiece. Then there is a workpiece positioning system, and for that purpose you may have stepper motors or servo motors for that matter, and here is the workpiece which will move left and right. Either the workpiece will move left and right or up and down, or you can move the laser itself by for scanning purposes on the whole surface of the workpiece. Now, let us see various types of the lasers. We have seen the working principle of the lasers, what are the problems with the long pulse lasers and what are the advantages of short pulse lasers. Now, what are the various types of the lasers, that is also important to know. Different types of lasers, you can see here basically two types of lasers are there. One is the gas lasers and another is the solid lasers. Now, in case of gas lasers, only two are shown over here. One is the excimer laser, whose wavelength varies from 193 to 351 nanometer, although this must have changed with the developments in the excimer laser in the recent past. Then you have a CO2 laser which has around 10 micrometer as the wavelength, and in case of solid state laser, the most popular one is the Nd:YAG laser, which has around 1.064 micrometer as the wavelength. Solid lasers are ruby and Nd:YAG lasers. These are the two different types of the lasers which are commonly used. These solid lasers, they cannot be used for heavy duty work, because power of the laser that you obtain from the solid lasers is comparatively smaller as compared to gas lasers. It is used for spot welding, for drilling fine holes, etc. Very important applications of this solid lasers is metrology, biomedical applications, material processing and similar other applications. And then you have the glass lasers, which includes helium neon lasers, CO2 laser, argon ion lasers and others. Now, gas lasers, in some cases you use light pointer. They are basically used for cutting, joining, etc. For light pointer, you normally use solid lasers also. Now, this is important to note here. In time scales, the lasers can be classified as follows: 1 into 10 raised to minus 3 second, that is known as millisecond lasers, microsecond lasers, nanosecond laser, that is 1 into 10 raised to power minus 9 second, picosecond laser 1 into 10 raised to power minus 12 second, and femtosecond laser, that is 1 into 10 raised to power minus 15 second lasers. Now, there are various hazards of the lasers. One should be knowledgeable to this, and based on the hazards or the other characteristics, the lasers have been classified as class 1 laser, which is a low power laser. Low level of damaging capabilities are there, or damaging radiation is there. Then class 2 laser, that is again low power lasers. They do not cause eye injury when you are looking at the lasers accidentally, but they can produce retinal injury with continuous intra beam viewing. So, one should be careful that they should not continuously view class 2 lasers, otherwise it may harm in some way or other your eyes. Then there is class 3 laser, which is the medium power lasers, a laser which is visible, which you can see with the eye, no eye injury within blink 0.25 second. That means, if you are looking at that laser, your laser is inside your or touches your eye for a very short period, say 0.25 seconds, there will be no injury. Injury is possible with binoculars or optical devices or by continued staring at the beam. Lasers viewed directly can definitely cause injury to the eye if it is class 3 lasers, class 3B type of the lasers. And then class 4 lasers, which are high power lasers, they need extra precautions and control measures to avoid any hazard to the operators or other people. So, one should know these characteristics and should observe precautions while looking at the lasers, otherwise they may be harmful to the operators or the human beings in some form or the other. This I have already explained. You have the gas lasers. Now, in this particular case, gases are recirculated and replenished, and I have already shown to you one of the examples where you were using folded, resonated or axial flow CO2 laser. Now, important point here is that CO2 lasers are high power lasers and they can give you as high as 1500 watts, that is 1.5 kilowatt, or in some cases even more than that power. For very high power, you can use transverse flow or gas transport lasers. Large amount of gas volume is required for that particular purpose, and beam is reflected several times before it escapes as a laser beam through a partially reflecting mirror. I have already shown to you that in place of 2 tubes, which I showed to you in earlier in the figure, you can use more than 2 tubes to get extra high power lasers. Computer control of the laser beam machining system to take advantage of high speed processing scanning. All the laser beam machining setups practically are computer controlled, and this is very much essential to have the computer control, so that you can take advantage of high speed processing using the CNC features of these machines, that is computer numerical control feature of these machines, and motion is given either to the workpiece or to the beam, or in some cases you can give the motion to both of them depending upon the workpiece requirement. Energy source providing initial stimulation should be powerful enough so that majority of the atoms or molecules of the lasing medium attain higher energy level, that is from P to Q or E1 to E3 or E0 to E3 level. Condition 2, that is also a requirement, that to produce a laser it requires a feedback mechanism. How the feedback mechanism functions I have already explained. Now, process characteristics. Some salient features of laser beam machining system are that it can machine through glass or optically transparent materials. It can machine in inaccessible areas wherever the beam can reach. So, it is very different from mechanical type of machining processes. It is not competitive with conventional techniques. Now, this is very important point to take note of, that one should not try to replace laser beam machining under the circumstances where you can do your work with the help of traditional machining processes, because traditional machining processes are very economical, low investment cost and comparatively fast. Laser beam machining should be used only in those circumstances where other processes which are more economical cannot serve the purpose. So, because laser beam machining machines are high capital intensive and also the operating cost is very high. One can imagine that the efficiency of the laser beam machining system is lower than 1%. So, you can think of that how much is going to be the operating cost. In future, it is going to be commonly used system on shop floor. Researchers are trying their best to improve the machining efficiency, reduce the cost of investment and definitely increase its applicability into the various fields of manufacturing processes. The ruby rod is less efficient at high temperature and it requires cooling. Laser system efficiency is quite low, as I have just mentioned. Normally it is less. However, efforts are being made to improve upon this. The expelled material in the form of the droplets in case of laser beam path continues to absorb the energy. Now, what happens that whatever is the expelled material from the molten material from the groove, when it again comes in contact with the laser beam, then it absorbs a large amount of the heat, and as a result of that the same material gets resolidified, again takes the beam energy and gets evaporated and then gets solidified and so on, and because of this process also the efficiency of the laser beam machining is quite low compared to other factors also. Laser beam machine component has low fatigue strength. It may be due to micro cracks and thermal residual stresses. I have already shown in one of the figures that micro cracks are developed during laser beam machining, and because it is a thermal process, high heat energy is produced at the workpiece beam interface. As a result of that, finally you end up the component having thermal residual stresses. Both these factors add to the reduced fatigue strength of the laser beam machine component. Another point is thickness of heat affected zone HEZ depends upon feed rate, that is the relative motion between the laser beam and the workpiece, gas pressure, nozzle tip distance, that is the focal point length, and sometimes also the focal point length, but not necessarily at every time that nozzle tip distance is equal to focal point length, no, and gas nozzle diameter, they also decide the thickness of the heat affected zone. Laser beam machining cannot be applied to the materials having high thermal conductivity and high reflectivity, as I mentioned in the beginning, especially the aluminum, copper and similar other materials having high thermal conductivity and high reflectivity cannot be easily machined by the laser beam machine. Many times laser beam machining system manufacturers recommend to use aluminum material as the machining table, so that whenever laser beam comes in contact with the aluminum table, it gets reflected and it does not machine the aluminum table, it machines only the workpiece. Laser beam machining is quite inefficient system, as I have mentioned, less than 1% or so, and machining efficiency is less than 1%. The question arises why. So, one of the reasons I mentioned that the droplets, when they come in contact with the laser beam, they get evaporated again and then they consume lot of the heat energy. There are various other factors where the heat energy gets lost, because of which the laser beam machining efficiency goes substantially low. Figure as shows the laser beam energy it utilized in various events, which make the efficiency lower and lower. A part of it is lost due to reflection and scattering from the workpiece surface. Definitely, how much is the reflection, how much is the scattering depends upon the surface characteristic of the workpiece. If it is highly reflective, large amount of reflection will take place, and if surface finish is not good, then lot of scattering will take place and concentration of heat will not be there. Then again the machining efficiency will go down. Some part of the heat is absorbed by the workpiece surface. Now, this particular diagram tells how the laser beam incident power is utilized. Some amount of the laser beam is lost due to the reflection, part of it is lost due to the scattering. Now, whatever amount is absorbed in the workpiece material surface, it is used for various activities, just as thermal diffusion. As you can see here, thermal diffusion loss is there, and then part of this thermal diffusion is utilized for melting the workpiece material, and this molten material is removed by the high pressure of vapor that are created in the groove or the cavity or the feature that is being produced. Now, part of this heat which is absorbed by the workpiece surface, it is utilized for vaporization of the molten material. So, when it is melting, it is consuming latent heat of melting, and when it is vaporizing, again it is taking latent heat of vaporization, and material is removed by way of either melting or vaporization and melting both, and substantial amount of losses may be there due to the radiation losses, because temperature produced during laser beam machining is quite high. As you can see here in this particular diagram, this figure indicates the process of laser beam drilling. You can clearly see there is a laser beam, and when this is removing the material, in the cavity plasma is being formed over there, and then you have the erosion front or the molten material, and which later on in many ways gets redeposited on the machined wall, and that is known as recast layer. Then there is the conduction of the heat, and other losses are also there which are not shown over here. But the important thing to note here is that in case of drilling, if you are expecting a straight sided hole in laser beam machining, that is not possible. As you can see here, it is non straight hole, bell shaped hole that is being produced by laser beam machining. Now, you can see here that you can also have a through cutting with the help of the laser beam, and you can clearly see here that laser beam is there, and as I have mentioned earlier, either beam can scan the workpiece surface or workpiece surface can move with respect to the laser beam depending upon the features available in the laser beam machining system. Now, here some of the things you can check which are common in earlier figure and this figure. Plasma formation is there, then coaxial jet is there, evaporation is taking place, and ejection of molten material is taking place, and heat is conducted away there, and molten layer is also there. Now, this is quite good for the case of through cutting, but if it is a blind cutting or grooving kind of the case, then you can see in the lower figure that the ejection of molten material is very essential. If this ejects out or it vaporizes, then only the laser beam will be able to machine it further and further, and so you have the scanning motion of the laser beam in the direction I have shown by arrow, or the workpiece can move in this particular direction, that is the reverse of moving of the beam, and then only you can create the groove in the workpiece surface. Now, as I mentioned in the earlier slide, that you are not going to get a straight sided hole by drilling using the laser beam process. Now, this particular figure tells you the shape and size of a hole drilled by laser beam machining, and these are the various features that you are going to get in the drilled hole using laser beam. As you can see here, A is the A dimension, A is the mid span diameter of the drilled hole, B is the recast layer, you can see over here, this is the recast layer shown over there, and then C is the exit diameter, the diameter at the exit from the workpiece surface, that is the exit diameter, and you can clearly see the difference between the A, C and E that is there. D is the hole depth, this is the through hole which has been drilled in the workpiece surface, and you can see this is the D, and then E is the inlet diameter, that is so. So, you can clearly see the diameter E, diameter A and diameter C, all the three are different. So, you are not really going to get a uniform diameter hole with the help of the laser beam machining process, or the one that you can get by mechanical means using a drill. Then you can see the surface debris which are the G shown over here, which we have seen in the figure photograph also, and then phi is the inlet cone angle, that is at the top shown over there, and then alpha is the taper angle of the hole being drilled. Now, this gives you an approximate idea of what is going to be the taper angle. However, this is not a straight sided hole or tapered sided hole, rather non-linear curved hole. So, it gives some some idea of taper angle, but not exactly it is the taper angle. Now, in this particular case, the effect of time on the thickness of the workpiece material that is being machined is shown over there, and you can see the diameter of the hole or cavity being machined is just 0.76 millimeter. Now, as time is increasing, the thickness of the hole being drilled or machined is also increasing, but after a certain time it becomes more or less constant. That means, there is no increase in the thickness, or it cannot further increase. There are so many other losses and other phenomena, because of which there is no further increase in the thickness or the depth of the hole that is being drilled. So, it indicates the limitation of the laser beam machining system, that it cannot drill very deep holes. Now, it shows pulse energy versus time. If you take a workpiece of a certain thickness and certain requirements or certain features, if you are having very high pulse energy, then the time taken for making that particular feature is low, but as the pulse energy increases, the time taken keeps on increasing, and it becomes more or less asymptotic after a certain pulse energy that you can see over here. That itself indicates that after a certain pulse energy, if you keep increasing, it is not there is a certain threshold value of machining or making the feature in the workpiece that will be taken in any case whatsoever is your energy capacity. Let us see the various applications of laser beam machining. Application of laser in material processing. Now, material processing may take place in various ways. One of them may be involving change of phase or state of the workpiece material. Another may be that there is no change in or phase, no phase change of the workpiece material. Now, when there is a change or involving change of phase or state of the workpiece material, you can have solid to vapor. Another one, you can have solid to liquid. Thank you very much.